Alright, so this isn't too bad of a problem. It starts out with part A, and this is just, do you remember the definitions? Let's see here. So, remember MP is S inverse M, where, S is equal to A set minus P, so that's already there. So this is the set M. Yeah, it's M cross S set, and we're going to mod out by an equivalence relation. That's defined as follows. M1 over S1 is equivalent to M2 over S2 if and only if there is some t in S such that t times, so here we have S2M1 minus S1M2 equals 0. And of course, when we say S2M1, that's because M is an A module, and S2 is an element of S, which is a subset of A. This is just the action of S2 on the module element M1. And of course, M1 and M2 are in M, and S1 and S2 are in A. And like I said here, T is in S, which is A set minus our prime ideal P. Okay, so that's what the set is. So here we make MP plus, and see here's 0 in a abelian group by addition M1 over S1 plus M2 over S2 is equal to M1 S2 plus M2 S1. I think that's flipped. Yeah. I think this should be like we have over there. It's S2M1 minus S1M2. Everything here is commutative, so we don't really need to worry about mixing things up. But the fact that this is a module, we typically, we're going to say that these are left modules. And so the element of A needs to be on the left. Okay, but anyway, so we have this, and we were dividing by S1, S2. And we also make MP and S. I'll write down an S inverse A module by the action. So if we let an element of S inverse A act on an element of MP, then this is just the action of A on M divided by S1, S2. So this, right, and so this makes MP an S inverse A module, but S inverse A is AP, so this is really an AP. Right, so MP is an AP module by this action, and right, that's the definition of MP, and this is how we make this a module over AP. Although, let's see here, MP is just the abelian group, because MP is a module, and then we have AP acting on it. Okay, so yeah, that's part A. And so then the next thing is part B. We want to have phi prime, show that fm is m is 0, blah, blah, blah. So scroll down a little bit, and see here. So let M be an element, a non-zero element of M. So here, define A. I'm going to use this for my ideals. It's similar to, like if you see this fancy P that the writer of this problem used, there's also a fancy A that looks sort of like this, but like really fancy. So I'm just going to write it like this. Anyways, let's make this the collection of elements of R, which act on this module element M by sending it to 0. I'm pretty sure this is called the annihilator of this. This is like the annihilator of the element M. So anyways, what do we know about A? A is an ideal because given A and B in this ideal, and any R in R, then AM and BM are both 0 because they're elements of the annihilator. And so this implies that A plus BM is, well, you just distribute it by how module actions work. But this is 0 plus 0, which is 0, and so this implies that A plus B is in A, and so we have closure under addition. And if we have the element RA acting on M, then we use associativity because associativity is given to us by the module action. So this is R acting on AM, but A is an element of this ideal A, and so it's 0. So this is just R acting on 0, which is going to be equal to 0. And so this means that RA is in A, and so we have, okay, and clearly, I guess we have to say this. 0M equals 0, which implies that 0 is in A. Although, no, we didn't need to do that because we could have just chosen this element, because 0 is an element of R. And so, yeah, and so we're good. So, yeah, this proves that A is an ideal. Let's see here. Since M is non-zero, 1 is not in A. Because if 1 were in A, then that would mean that 1 applied to M is equal to 0. But 1 applied to M is just M, and so that means that M is 0, which contradicts that M is not 0. So the fact that M is not 0 implies that 1 is not in this ideal A. So A is a proper ideal. Then there is, okay, so then by the axiom of choice, R has a maximal ideal. Remember, this is a really important fact that rings, if you assume the axiom of choice, then any ring has a maximal ideal, a maximal proper ideal. R has a maximal ideal P. P is prime. That's another fact that in any ring, maximal ideals are prime. Do you need commutativity? I forget, but we're in a commutative ring here, so I really don't care that much right now, even though I should know it. But yeah, so we have a maximal ideal, and P is prime because maximal ideals are prime. And okay, so A is a proper ideal of R, and so it must be contained in the maximal ideal P of R. Okay, and so this is kind of how we find our prime ideal P, is that we use we just kind of, we didn't really have to do much work to find this prime element P. By the way, that this prime, oh well, okay, I just realized, let's use this fancy notation because that's what's used in the problem statement, and I want to try to be a little consistent with that. Okay, so this is going to turn out to be the prime ideal that we want to find. We want to find a prime ideal such that phi p applied to m is non-zero, and this is going to be the one to use. And this should be sort of something you should think to use, or at least something you should think to try at first, because in general you don't know what prime ideals of rings look like. They could be really weird, and especially if the problem's not asking you to prove that every prime ideal P is such that phi p of m is non-zero. It's asking you to find one, and this is like the one of the only ways that I don't know. There might be other ways, but at least this is certainly the easiest way to find prime ideals. Is to use the fact that every ring has a maximal ideal, and that maximal ideal is prime, and thus you always have a prime ideal. It might be zero, but whatever. It turns out there, just real quick, it turns out there is some stuff about like prime ideal being zero. If that ends up being the maximal ideal, then I think there's something about like this, something about zero divisors comes into play here. But anyways, so we have a zero, we have a maximal prime ideal P, and A is contained in P. So that's really what this paragraph was about. It wasn't so much in finding P, because we were basically just like half a sentence. We're like, hey, axiom of choice, R has a maximal ideal P, and P is prime. What we really needed to do was to prove that the annihilator of M is contained in this maximal ideal, so long as M is non-zero. And that's really, let's see here, I tried to do this problem recently, and it turns out I did this in a class, but that's the key step that I was missing. Like I sort of thought to look at the maximal ideal, because I was like, oh, well, that's something I know could potentially lead to something useful, and if I want to find a particular prime ideal, that's a great way to start. But yeah, what you really need is you need to be conscious of the annihilator, and think about that a little bit, and then realize, oh, the annihilator is contained in the prime ideal, so long as M is non-zero. Okay, I've rambled like way too long about that point, so let's continue. So now we're going to do contradiction argument. So assume for contradiction that phi p of m is equal to 0. So what can we conclude? Phi p of m is equal to m over 1 by definition, because that's just the definition of this map, phi p of m. You just send everything to the thing over 1. And that's that's sort of like how you think of integers as rational numbers, is you just think, oh, well, this integer you just divide by 1 and you have a rational number. So this should be very familiar, or like it shouldn't be weird that you can just divide by 1 to move something from the ring into its localization. But anyway, so this is by definition. So M1 is, see here, so M1 is equal to 0, 1 in MP, i.e. M1 is equivalent to 0, 1, i.e. there exists some element S in R set minus P, which of course is equal to capital S, just in parentheses there, such that S of 1 applied to, let's see here, we have 1 applied to M, minus 0, no, minus 1 applied to 0 is equal to, what did I write down here? Oh, is equal to 0. Oh, yeah. I have equal to 0 here, and then like there's a, on the next line I have something equal to the empty set. And I'm like, that doesn't make sense. So, i.e., so let's see here, you just do this and it's just s applied to m equals 0. So, s is an A, which is a subset of P, which means that, let's see here, S is in, it's in P by this previous thing, but it's also in our set minus P, which is equal to the empty set. So S is an element of the empty set, but the empty set does not have elements because it's empty. So this is a contradiction. Can't quite fit the rest. Thus, phi p m is not equal to 0. Hence the desired result holds for, or in particular, when P is the maximal ideal of R. And yeah, there we go. So this completes our proof.